10.3, using chords. Can I use chords of a circle to find lengths and arc measures? Let's take a look at our first theorem, congruent corresponding chords theorem. So if I'm in the same circle or congruent circles, if I have congruent chords, like I have these red, then I want to prove that my arcs are congruent. We're going to do that by trying to prove the triangles are congruent. So I know that all these are congruent because they are radii. So the two triangles will be congruent by SSS. Now, then I will get this angle congruent to this angle. That's corresponding parts. And once I get the angles congruent, I know these arcs are congruent because they have the same measure. These angles are congruent. The measures are here. They're in the same circle, so I know we have congruent arcs. The converse, what if we start off with congruent arcs? You can see I have congruent arcs right here. And once I have congruent arcs, I know these angles are congruent, these central angles. And I also know that I have all these radii congruent. So that means the triangles are congruent by SAS. And once the triangles are congruent, I can say the chords DC and AB are congruent. Our next theorem is the perpendicular chord bisector theorem. It says that if you have a diameter and that diameter is perpendicular, something very interesting happens. That diameter will bisect the chord and its arc. Let's go see how that's done. So this is perpendicular, and then I draw the radii to create these triangles. I know this radius and this radius will be the same. I know they're going to share this side right here. So the triangles are going to be congruent by HL. Once the triangles are congruent, I know that this side right here is congruent to this side by CPCTC. I also know that this angle is congruent to this angle, which forces this arc right here to be congruent to this arc right here. And that's my last piece right there. All right, let's go ahead and practice. Oh, we're going to do one more theorem. This is the converse of the previous theorem. If I see a chord and it is a perpendicular bisector, I want to demonstrate to you that it must be a diameter. Now remember, every point on this perpendicular bisector has to be equidistant. So there's some point where this distance is the same as this distance right here. And so we know somewhere along here there's a point, and it's going to be called the center that's equidistant. And that's exactly what a radius is. So these two are a radius and a radius. And you will know a radius is hooked to a center, and a center is part of a diameter. So that's why that has to be a diameter. Okay, let's go ahead and practice a problem. First, I see that these are congruent circles. I can see that because this radius and this radius are congruent, so I know I have congruent circles. I also know I have congruent chords. Chords are congruent. So the theorem says then the arcs must be the same. So this arc right here has to be congruent to this arc. And since this arc has 80 degrees as its measure, this one has to have 80 degrees as its measure as well. All right, let's go ahead and find this one. I'm in a triangle and I see a diameter that's perpendicular to a chord. So I know that it's going to bisect the chord. It's going to cut it in half, which means this side will be 7. So HK will be from H all the way to K, which will be 14. All right, I also know that these chords have been bisected. So I know 11x is equal to 70 plus x. And so that's going to make 10x equal to 70, so x is equal to 7. So this is going to be 77 degrees, and of course this is going to be 77 degrees. I want to find arc, the measure of arc, HK, so I'm going to use arc addition, and I'm going to add those two arcs together, and so the answer is going to be 154 degrees. All right, let's take a look at an applied problem. We have 3 bushes in a garden. Where should we place the sprinkler so that it's at the same distance? So somehow the sprinkler has to go somewhere around here so it can flow and water these 2 things. So we can use some geometry to do that. We know that we can draw a segment here, just like we've done right here, and we can draw the perpendicular bisector. So somewhere along this perpendicular bisector lies the center. We don't know where, but somewhere along here. So let's go ahead and join these 2 bushes as well and draw its perpendicular bisector. And somewhere along here is going to be the center because it represents a diameter. So where these 2 diameters meet is going to be the place where you want to set the sprinkler. All right, let's take a look at an Archaeologist application problem. Suppose we have a partial dish right here, and we can measure this chord right here. We can measure it 7 inches, and we can measure this 7 inches. All right, and then we know that this distance here is going to be 6 inches, and this distance will be 6 inches. The question is to find the diameter of the plate. So I'm going to draw a radius. If I can draw a radius, then maybe I can figure out the diameter. So this is my radius, and I know this whole thing is 7, so I know this is going to be 3.5 inches, and I'm going to use the Pythagorean theorem. C squared is equal to A squared plus B squared. My hypotenuse is R, that's what I'm looking for. I know this is 3.5 squared plus 6 squared, so R will be equal to root 3.5 squared plus 6 squared, and that'll be approximately, now remember this is only my radius. As soon as I figure out my radius, then it'll help me find my diameter. So on my calculator I have about 6.946 and some other decimals. I am now going to multiply it by 2 on my calculator, and then I'm going to get 13, and they want to the nearest tenth, 13.9, and then this is going to be labeled inches. All right, your turn. Go ahead and stop the screencast and see what you can do. Here are the answers. I tried to write the theorems out here as well that you're using. Okay, let's take a look at another theorem. It's called the Equidistant chords theorem. Okay, it says that in a circle, if the chords are congruent, then they are equidistant to the center, and the converse. Okay, so let's prove one direction. Suppose we have 2 chords that are congruent. So I have this thing right here. These 2 chords are congruent. This whole chord is congruent to this whole chord. And I'm going to draw a perpendicular here, so that's going to cut it in half. So I know that since all of these are congruent, these little pieces are congruent right here. And I also know, that's what it's being said right here. I also know these radii are congruent. And that's what's being stated right here. So the triangles are congruent by HL. Once the triangles are congruent, then I know these pieces, this distance E to F and this distance E to G are also congruent by CP, CTC. Now the rest right here is just the converse. So after this sentence right here, then it proves the other direction. All right, let's see what we can do. So I have a picture here, and it looks like I have chords that are congruent. So I know this whole thing is 16, and I know this whole thing is 16. So in the same circle, the chords are congruent. So if the chords are congruent, they are equidistant to the center. So that means this distance is equal to this distance. These are the shortest distance. So I'm going to write 2x is equal to 5x minus 9. So this is 3x is equal to 9, and therefore x is equal to 3. Now it wants me to find the radius. Okay, so I know this length is going to be 2x, so that means this is going to be a 6. This distance is going to be half, which is 8, and they want me to find the radius. So I could either use a Pythagorean theorem, but this looks to me like a 3, 4, 5 triangle. And I have the 6 and I have the 8, so I know my radius has to be 10, and that's what I was looking for. Okay, your turn. Go ahead and stop the screencast and see what you can do. And here's the answer. Again, you have to set the distances equal to each other, and once you do that, you draw your radius so that you can see your right triangle and try to figure out the rest.